Okay, so the second part is mainly about research and like advice to students.
Okay.
So the first part is biophysics specific, and it's mainly about your main research interests and projects and how they evolved over time. So if you can give us an overview and then a little bit of a detail about each project that are currently working in the group.
Sure. Okay, that's quite a bit.
Okay.
So most of my research has something to do with RNA or DNA these days.
Okay.
So there are one main direction is to try to understand the interactions of RNA and proteins, specifically RNA that forms these secondary structures through base pairing. Proteins want to bind RNA, and they either are looking for unpaired bases or for paired bases. In each case, the secondary structure matters for the protein, and so understanding how the protein RNA interactions with the RNA affect each other. This is sort of one of the things that my lab has been working on for the last 10 years or so. Okay. Then another broader area is DNA origamis. Okay. So there you're building structures from DNA molecules, and then you're trying to understand their mechanical properties, their dynamics, and how you can change those by changing the design. So this again is about modeling base pairing, so it's actually quite closely related to the RNA folding. And then there is a genomics side where we work with several collaborators in the biological or life sciences and trying to develop better methods to analyze high throughput sequencing data sets.
I see.
So when I started out at OSU, I sort of came in already working on RNA, but more looking at it as a disordered system, looking at phase transitions, calculating critical exponents, so more sort of traditional stat-mech kind of questions. I certainly have evolved more and more towards really trying to answer biological questions and things that are biologically relevant.
Okay.
And then the fact that this whole field of genomics was really changed by the advent of high throughput sequencing is also something that created quite a shift in my research program.
Okay. So the next question is more about like graduate students in the group and like their future careers. So based on your experience, what are the main future careers for biophysics graduates in academia and in industry?
Right. I mean, in academia, obviously the traditional route is to, do a postdoc after the PhD and then apply for faculty positions. And there are definitely some of my students that have chosen that route.
Okay.
But I think, so in theoretical biophysics, we tend to work fairly closely with real data. Okay. So there are definitely careers in industry that are related to that. So data analysis kind of positions, as well as positions where just programming is a relevant task. And there are students that have gone into biotechnology companies where they sort of more directly use that bio experience. But I have students that have gone on to just technology companies where it's just about the programming, as well as students that use the biology per se, and students that do data analysis of large data sets that have maybe nothing to do with biology nowadays. Okay. And any of those really, a PhD in theoretical biophysics can prepare one for.
So, following that, what are things that you wanted to know when you were a graduate student, or things that could have been helpful when you were a graduate student to you? Especially like, this is like an advice to students interested in doing a PhD in biophysics overall, if you have something in mind.
So advice to students that want, so if I could go back, and again, I mean, in my PhD, I didn't even do biophysics yet. Yeah. So it's not something that I was missing as a PhD student, but if I could go back now, I would like to do some experiment,
Okay.
not because I think I would want to become a full-time experimentalist, but I think it would be very helpful to know even more than just by talking to people how experiments are being done.
Okay.
So I think that's one piece of advice, to sort of be broad in your training. The other advice is to really learn the language of biology. I mean, one thing that I have a very hard time with is when both physicists give a talk and they say basically, well, I don't understand the biology, you have to ask my biology collaborator about this. I've also seen it the other way around, where biologists that work with computational people say, well, I don't understand what happened in the computation, you have to ask my collaborator. And I find this actually quite problematic. And so I would really encourage students to learn everything around their project. And of course, they can't do everything and they can't know every detail, but to really learn as much as possible about all aspects of the project.
I see.
And so to be able to answer questions about that and really understand the big picture of what's going on.
So the next part is mainly about like general physics, not necessarily biophysics. And the first question is like, how has the field of physics changed since you started your PhD? And in what aspects do you see the greatest need for improvement, in your opinion?
Okay, I mean, it has been a while since I got my PhD, and so it is, I think, quite amazing to see how different fields, change direction. So when I was a PhD student, the question if neutrinos have mass was, for example, not known.
Okay.
I have seen the cold atom physics coming out of nowhere and becoming a huge field. Certainly nowadays, quantum information science becoming a real big field. And I think in general, sort of in AMO physics, I think there was maybe some time where it was not so prominent, and now this is a very prominent area again. But I think that's true of many fields of physics, that over several decades, really completely new things come up, and things that were maybe a little out of fashion at some point suddenly come because technology changes. Really are generating totally new questions, and
that's true. So is there a specific aspect, like overall, that you think would need some kind of improvement, or
for the field of physics as a whole? That's a very difficult question.
It's a very broad kind of question.
I mean, physics has been, it's sort of a random walk at some extent, right? That one cannot plan, and so I think this idea that one, that the community as a whole works on many different problems because you do not know where the next big thing is going to happen. I think is a good strategy.
Okay.
So
to just keep it random.
Well, I mean, of course, it's not completely random.
Yeah.
There's a finite amount of resources, and of course, through peer review and so on, one has to, at least pick some directions that seem promising. But on the other hand, also not sort of hyper focusing on a few things is important. I think that's something that the physics community has been doing pretty well in.
The next one is about like, what specific skill do you think is the most relevant for researchers in your field, especially right now?
Right. So the most important skill is really motivation.
Okay.
I've never seen a grad student fail because they couldn't do what they were trying to do. But I've seen grad students fail because they were not motivated enough to do.
Okay.
And doing science is pretty hard. There are lots of setbacks. Your program fails, your experiments don't work. Even once you think it all works, you submit it to a paper or to a journal, and the referees have a very different idea from yourself about your work. So there are all these setbacks, and I mean the only way to get over these setbacks is if you really intrinsically, want to understand what's happening, want to figure it out, and to have that kind of motivation. I think that overall in science is probably the most important factor for successful scientists. Now, in my area specifically, yes, having good programming skills or developing good programming skills it is an important factor because that's our daily bread and butter work in a computational lab. So without being able to do the plumbing, you can't actually succeed in the science. But then, as I already said, this idea of really trying to understand the biology behind things also is an important factor. But again, motivation, I think, is the number one factor.
Following up on that, what are the most important qualities, in your opinion, of a graduate student? Or what do you value the most pertaining to training students?
Right.
To training students?
Yeah, so I think this comes from this motivation as the main factor. So a student being excited, and I think a student being proactive is very important.
Yes,
so when students start, they don't have much experience and they need more guidance. But even then, it is important that students try to find papers, read papers, try to come up with their own ideas at the beginning at a maybe smaller level, and then as they go through their training as a PhD student, they're ready basically when they can come to me and say, well, here's a project where there's an open question, and this is what I want to work on. So I mean, that's basically when the PhD training was successful, because that's really what the PhD is about. It says that you can work as a scientist, and what scientists do are identifying problems that are important problems that can be addressed with methods that either exist or are likely to be able to be developed.
Yeah. So I think following up on this part, the goal of a PhD is, so the next question is, with many physicists by training leaving physics research to pursue more profitable avenues, do you see this as a problem, or is the fact that physics program train the students to be general problem solvers a good thing to the community? So the overall goal of a PhD.
Right. So I absolutely think that it's essential to train people that go outside of academia to be good quantitative problem solvers. So one of my former graduate students told me that when people ask him, well, why are you working here as a physicist? He tells them that physics is really the liberal arts education in the sciences. And I think that's a very good way to put it, because you are trained as a general quantitative problem solver. And we need those problem solvers in many places in society, not just in academia. And I think it's maybe even more so in the life sciences, where there is a really strong push from even the funding agencies to make sure that training of students includes training in soft skills that are geared towards industrial settings, and not just thinks of grad students as future professors. But I think physics could actually learn a little bit more from the life sciences in that regard. There is only a finite number of physics professor positions, and a physics PhD should really train for many possible avenues where having this physics PhD is really going to be very useful in terms of doing something great in an industrial setting, or in a government setting, or in a patent law setting, or any of those above.
I see that.